This lesson is about implicit differentiation. In this lesson, you must be able to determine the derivative of a function that is given either in the explicit or in the implicit form. Recall from algebra that a function may be defined explicitly or implicitly. A function is said to be defined implicitly if we can write the function in the form y is equal to a function in x. So an example will be y is equal to 2x minus 3. However, there are functions where we cannot write y explicitly in terms of x, and thus we work with what we call the implicit form of the function, where the terms of the function are in x and y. So we have in general the form of the function r is a function of xy equal to 0. So here are some examples of functions given in the explicit form. We have y is equal to 3e to the x, where clearly we define y as a function of x. Or we have y is equal to 5 minus sine of 4x. Another example would be y is equal to 7x to the fourth minus 5x squared plus 2x minus 1. Or we can have y defined as ln of the square of 2x minus 4. Examples of function given in the implicit form would be the following. We have y is equal to 3 times e to the x plus y. So as you can see here, we have terms that are expressed in x and y. Or we have 5 minus x squared y plus 3xy squared is equal to 0. Again, as you can see, there are terms here that would involve both x and y. Or we have x squared plus 4xy squared is equal to 4y. Or we have the form tangent of xy is equal to 2 plus xy. If the function is given in the implicit form, there is really no need to write it in the form where explicitly we define y simply in terms of x. Using a function in the implicit form is advantageous whenever we cannot possibly separate the y from the x's. In general, it is not necessary to solve an equation for y in terms of x. For the purpose of differentiating a function given in the implicit form, we can determine the derivative using implicit differentiation. So the steps in implicit differentiation are as follows. We differentiate both sides of the equation with respect to x, and then we collect all the terms with dy dx on one side of the equation. Then we factor out dy dx from among those terms with a dy dx factor, and then solve for dy dx in terms of x and y. To illustrate how implicit differentiation is done, let us work on the following examples. Differentiating on 2x cubed y minus 2xy cubed is equal to 33, determining what is y prime. So for our solution, using implicit differentiation, this would require that we differentiate both sides of the equation with respect to x. Thus, we have the derivative with respect to x of 2x cubed y minus 2xy cubed equal now to the derivative with respect to x of 33. Now, in differentiating these expressions here, take note of the product rule for differentiation. because we will be treating 2x cubed y as product of 2x cubed and of y. In the same way that we will be treating 2xy cubed as a product. So if we are now to differentiate the left member, then the derivative would just be equal to 2 times the derivative of x cubed y treated as a product of the factors x cubed and y. Hence, the derivative would be given by x cubed times the derivative of y with respect to x plus the product of y with the derivative of x cubed given by 3x squared. Now, as to the derivative of negative 2xy cubed, this would result to having a negative 2 times the derivative of xy cubed given by x times the derivative of y cubed. Now, in differentiating y cubed, we will be treating it as a u to the n form, whose derivative is done this way. So, this now would give us, for the derivative, 3y squared times y prime. The second term will be y cubed times the derivative of x, which is equal to 1, and this left member would equal 0, the derivative of the constant 33 with respect to x. So if we are now to multiply the factors as indicated, then we will just have a 2x cubed y prime plus 6x squared y minus 6x y squared y prime minus 2y cubed is equal to 0. And from among these terms, we will be combining the terms with y prime. And this will just be the terms 2x cubed y prime minus 6x y squared y prime, equating it to 2y cubed minus 6x squared y. And factoring out y prime here and solving for y prime, then we will come up with, on the left, product of y prime with 2x cubed minus 6x y squared equated to 2y cubed minus 6x squared y. And solving for y prime will just give us the ratio of 2y times y squared minus 3x squared, that is coming from this expression here, factoring out 2y, which is the common factor. Now that should be divided by 2x times x squared minus 3y squared. Again, this is coming from the expression 2x cubed minus 6x y squared, factoring out 2x, which is the common factor. So from there, we simplify now y prime by dividing 2 with this 2 here, and write y prime in terms of the ratio of the product y times y squared minus 3x squared divided by the product x times x squared minus 3y squared. In this example, we would like to determine y double prime given the function 3x squared plus 6y squared is equal to 17. Again, we will be applying implicit differentiation so that we differentiate with respect to x the left member 3x squared plus 6y squared, equating it to the derivative with respect to x of 17. So to differentiate 3x squared plus 6y squared, we will be using the rule to differentiate the power. So that will just give us a 6x plus 12y y prime, and on the right is 0. So solving now for y prime, we will have 12y y prime equal to negative 6x, and y prime will be equal to negative 6x divided by 12y, or simply we have y prime is equal to negative x divided by 2y. But this problem requires y double prime or the second derivative. Hence, we need to differentiate with respect to xy prime, or differentiating with respect to x the negative of x divided by 2y. With this, we will be applying the rule to differentiate a quotient as given here, and this will simply give us y double prime equal to 2y times the derivative with respect to x of negative x minus the product of negative x with the derivative of 2y divided by the square of 2y. Differentiating now, we will have the derivative with respect to x of negative x being just a negative 1, and for 2y, we have 2y prime. But recall that y prime is equal to negative x divided by 2y, so that this complex fraction here will simplify now to this expression, having 2y times negative 1 minus x squared divided by y divided by the square of 2y. Okay, we further simplify. When we combine the terms of the numerator, the LCD will be y, and the numerator will transform to negative 2y squared minus x squared. Hence, we have this fraction for y double prime. But we can express this numerator in terms of the negative of 2y squared plus x squared, recognizing that 2y squared plus x squared is just 1/3 of this one. So we can equate now that expression to 17 divided by 3, so that from here we will have y double prime equal now to negative 17 over 3 divided by y times the square of y times 2, or we have y double prime equal to negative 17 divided by 12y cubed. Again, to recap our discussion, the derivative of a function can be determined using either the explicit or the implicit form of the function. That the higher order derivative of a function can also be determined using implicit differentiation.